Hello everyone, I'm Himanshu Asnani from Department of Mechanical Engineering and I'm here to discuss with you on the subject Material Science. The subject code is ME207, unit number 5 in the series and lecture number 30. Today's topics are corrosion and various types of corrosion. The learning objective for today's lecture is to provide the students with a basic understanding of corrosion, various types of corrosion, and learning outcome of today's lecture will be students have learned the basics of corrosion, various types of corrosion, and students understood various types of corrosion. Let's start the lecture with the corrosion. Okay, what actually the corrosion means? So most materials, to one degree or another, experience some type of interaction with a large number of diverse environments. So such interactions with environment impair a material's usefulness. As a result, deterioration of its mechanical properties takes place, like ductility and strength and appearance properties. Okay, so the control of corrosion and erosion or chemical attack in service or to prevent of surface decarbonization during processing or heat treatment. So we should take care of this. The corrosion. Corrosion is defined as the destructive and unintentional attack of a metal. Okay, you can say corrosion, you can define it as a destructive and unintentional attack of a metal. It is electrochemical and ordinarily begins at the surface. Okay, so you can again, I am telling you once again that corrosion, you can define it as the destructive and unintentional attack of a metal. The problem of metallic corrosion is one of the significant proportions. The problem of metallic corrosions is one of the significant proportions in economic terms. It has been estimated that approximately 5% of an industrialized nation's income is spent on corrosion preventions and the maintenance or replacement of products lost or contaminated as a result of corrosion reactions. So you can understand that what effect does the corrosion have on the nation's income. The estimates are like that, and approximately 5% of the industrialized nation's income is spent on corrosion prevention and the maintenance or replacement of products lost or contaminated as a result of corrosion reactions. So the consequences of corrosion are all too common. So familiar examples include like the rusting of automotive body panels. This we have seen in our day-to-day life very commonly. Okay, the like rusting of automotive body panels and the radiators and the exhaust components. You might have also visited any junkyard. So in the junkyard, you might have seen such kinds of examples very common, like rusting of automotive body panels, radiators, and exhaust components. Okay, so in metals, there is actually a material loss either by dissolution, like with corrosion, or by the formation of non-metallic scale of film, that is oxidation. Okay, so the common examples that we have faced in normal day-to-day life is like the side like rusting of some automotive body panels that you might have seen. And if you talk about metals, then you can say that there is actually loss, material loss, either by dissolution, that is corrosion, or by the formation of non-metallic scale of film, that is oxidation. You can see in the diagram also the picture of like oxidation is sorry, not we can say a corrosion is there on the screen for your example. Okay, so let's go to the next slide. The following types of corrosion are significant. Like one is the bad corrosion, second is electrochemical corrosion, third is galvanic corrosion, and fourth is the high temperature oxidation corrosion. Okay, so let's discuss all upon them. Now, when you talk about dry corrosion, then you can see that in the diagram also, it's just like in the air it is happening. Okay. Now, the ferrous alloys that get rusted at high temperatures forms scales and oxides. So one can prevent this corrosion by adding alloy elements which are resistant to corrosion in some metals and also have the properties at of high temperature surfaces. Okay, see you can see that the ferrous metals they are getting rusted at high temperature. Okay, and They form scales and oxides. Okay, and if you want to avoid this kind of corrosion, then you can have some add some alloying elements which are resistant to oxidation. Okay, and also have some good properties of working at high temperature. So when liquids metals flow past the other metals, this high temperature corrosion also occurs. So essentially, a corrosion reaction is a process of mass transfer and is not dependent upon local cell potentials for its driving force. Okay, it is not dependent upon local cell potential for its driving force. So truly speaking, the corrosion is due to the tendency of the solid to dissolve in the liquid metal up to the solubility limit at a given temperature. Okay, they say the corrosion reaction is a process of mass transfer. It is not dependent upon the local cell potentials for its driving force. So the corrosion is due to is the tendency of the solid to dissolve in the liquid metal up to the solubility limit at a given temperature. So we may note that the liquid metal attack may either form a simple solution of the solid metal, a compound, chemical compound, or B, the selective extraction of one of the components metal in a solid alloy. It occurs when there is a concentration gradient or temperature gradient within the solid liquid system. Now, serious damages by liquid metal attack has been reported in heat exchangers carrying these liquid coolants. So, a portion of the solid goes into the solution in the liquid as the solid container, usually copper tubings, and approaches equilibrium within the liquid metal coolant in the hot zone of the heat exchanger. So the solids try to deposit on the walls of the heat exchanger tubes as the liquid moves to the cooler part, okay, of the heat exchanger. And obviously the hot zone is continuously corroded and the cold zone becomes plugged with the deposited corrosion products. So one can prolong the life of the heat exchanger by the addition of certain inhibitors to the liquid alloy to form protective films to prevent high temperature corrosion. Okay. Now, like the next is that electrochemical corrosion. This is also a very important kind of a corrosion. Now, this kind of corrosion this develops in liquid electrolytes like moist atmosphere and salt and fresh water, aqueous solutions of salts, alkalis, and acids. I repeat, this electrochemical corrosion. You can say that this kind of corrosion develops in liquid electrolytes and moist atmospheres and soil and salt and fresh water and aqueous solutions of salts, alkalis, and acids. So electrochemical corrosion is characterized by the appearance of an electric current and dissolution of the metal due to its electrochemical interaction with the electrolyte. I repeat, due to its electrochemical interaction with the electrolyte. So there is a transfer of electrons from one chemical species to another. Okay, so metals atoms characteristically lose or give up electrons in is called an oxidation reaction. The surface of a metal is electrochemically inhomogeneous so that when the metal is placed into an electrolyte, this leads to the formation of microgalvanic corrosion cells. Okay, what they say in this, what happens? See, this kind of corrosion it develops in normally liquid electrolytes and moist atmospheres and soil and salt and fresh water and aqueous solutions of salts, alkalis, and acids. So this there is a transfer of electrons from one chemical to one chemical species to another. Okay, what happens in this? These metal atoms. Okay, how this transfer takes place? This metal atoms they characteristically lose or give up electrons in what is called as an oxidation reaction. So the surface of a metal is electrochemically inhomogeneous. Okay, so that when the metal is placed into an electrolyte, so this leads to the formation of micro galvanic corrosion cells. You see in the figure in the next sheet. So in some proportions of the surface which are called as anodes, there occurs reactions of the type 1 and the other portion other called as cathodes. You know the cathode and anode are there in this. So the portions are just called cathode or the type 2, second, and 3. So you can see this figure with the formation of scheme of corrosion cell, it is shown. Okay, in the figure you can see there's a metal, there is an electrolyte, and how the reactions are going. So you can see in these reactions also how this transfer of electrons is taking place. Okay, so this you can see that here the Me is represents the hypothetical metal. It's called as hypothetical metal. So examples in which the metals oxidize are like Fe gives Fe2 plus 2 minus, and aluminum is long Al3 plus 3 minus. So this is how they oxidize. Okay, now let's go to the next slide. The site at which the oxidation takes place is called as anode. So remember one thing, the site at which the oxidation is taking place is called as anode, and oxidation is sometimes called as anodic reaction. Now these are relative terms that which you need to understand. The site at which the oxidation takes place is called as anode, and the oxidation is sometimes called an anodic reaction. So the electrons generated from each metal atom that is oxidized must be transferred and become a part of another chemical species in what is termed as reduction reaction. What is called as reduction reaction. I repeat once again, you make it a good point. The electrons generated from each metal atom that is oxidized must be transferred to and become a part of another chemical species in what is termed as reduction reaction. So other reduction reactions are possible depending on the nature of the solution in which the metal is exposed. You can see the reaction and underneath also written. So the important point is that here from this thing that the electrons generated from each metal atom is that is oxidized must be transferred to and become a part of another chemical species. Okay, and what is termed as reduction reaction. So this is something that is needs to understood. So for an acid solution having dissolved oxygen, the reduction reaction may probably occur. For a neutral or basic aqueous solution in which oxygen is dissolved, reduction reaction given by this equation 2 that we just took place in the hand will take place. Okay, the reduction reaction that was shown in the equation 2 backhand will take place. So any metal ion present in the solution may also be reduced. For ions that can exist in more than one valence state, that is multivalent ion, reduction may occur in accordance. Like this is like Men plus this electron. It gives you Men plus 1. Okay. So you can understand that for ions that can exist in more than one valence state, that is multivalent ions, reduction may occur in the accordance by this. You can the equation is given in front of you. Men plus 1 minus gives Men plus 1. In which the metal ion decreases its valence state by accepting an electron. What happens? The metal ion it decreases its valence state by accepting an electron. So it is also possible that a metal may be totally reduced from an ionic to a neutral metallic state. You can see in this equation, Men plus 1 gives Men minus gives Me. So here it is reduced to a neutral metallic state. Okay. The location at which the reduction occurs is called as cathode. Now the location where the reduction is occurring is called as cathode. So you may note that two or more of the reduction reactions may occur simultaneously. So as long as the corrosion cell remains open, the reaction at the cathode and the anode portions proceed at the same rate in both directions. That is, they are reversible. What they say, as the corrosion cell remains open, sorry, as long as the corrosion cell remains open, and the anode and the cathode portions proceed at the same rate in both. An overall electrochemical reaction must consist of at least one oxidation and one reduction, and will be the sum of them. What they and will be the sum of them. So you may note that often the individual oxidation and reduction reactions are termed as half reactions. Note that often the individual oxidation and reduction reactions are termed as half reactions. Okay. So the basically the thing is that as long as the corrosion cell remains open, the reactions at the anode and the cathode portions proceed at the same rate in both directions. That is, they are reversible. However, there can be no net electrical charge accumulation from the electrons and ions. That is, the total rate of oxidation must be equal to the total rate of reduction. So obviously all the electrons generated through all the electrons generated through oxidation must be consumed by reduction. To make it clear, let us consider an example in which the zinc metal is immersed in an acid solution containing H plus ion. So you can say that some regions on the metal surface, zinc will experience oxidation or corrosion. Like Zn gives Zn2 plus 2 electrons. So zinc, being a metal, is a good electrical conductor, and the electrons liberated in equation number 9 may be transferred to an adjacent region in which the H plus ions are reduced. What is there? In the adjacent regions at which the H plus ions, these are reduced in accordance with like 2H plus 2 electrons with H2 gas. When no other oxidation or reaction occurs, the total electrochemical reaction is just the sum of equation number 9 and 10. That is Zn plus 2H plus gives Zn2 plus H2 gas. So another example, we can consider the oxidation or rusting of iron in water which contains dissolved oxygen. So this process completed in two steps. The first step is like Fe oxidized to Fe2 plus, okay, or as in FeOH2. That Fe is half of O2 plus H2O gives Fe2 plus 2HO minus gives then FeOH2. So in second step, the Fe3 plus is FeOH3 in accordance to 2FeOH2 plus half O2 gives H2O plus H2O gives 2FeOH3. So we know that a compound FeOH3 is all too familiar rust. Okay, this compound FeOH3 is all too familiar compound rust. So high temperature oxidation of iron processes as follows. You can see the reaction is 2Fe plus O2 gives 2FeO and plus O2 gives metal oxide. So you can see that 2Fe plus O2 minus gives FeO. Fe2 plus O2 minus gives FeO. That is metal oxide. Now, silverware gets tarnished in the presence of atmosphere by hydrogen sulfide. What does it say? Silverware get tarnished in the presence of atmosphere by hydrogen sulfide. Reactions like Ag plus H2S gives AgS plus H2. So these reactions are common to all metals and the scales formed are uniform throughout the surface. Let me say these reactions are common to all the metals and the scales formed are uniform throughout the surface. That is, a direct attack proceeds uniformly over the entire surface of the metal. So as a consequence of oxidation, the metal ions may either go inside the corroding solution as ions, that is reaction number 9 that you see, or may form an insoluble compound with non-metallic elements. That is reaction 13 that you just see. So always knew that we should understand the silverware get tarnished in the presence of the atmosphere by hydrogen sulfide. Okay. You can see the reaction that is shown. The reaction is like log. So here the silverware is getting tarnished in the presence of atmosphere by hydrogen sulfide, and this reaction is there with you Ag plus H2S with AgS plus H2. Okay. Now the third one is the galvanic or the two metal corrosion. This is also very important kind of corrosion. Okay. Here also you have electrolyte and an anode and cathode having their minus and the plus charges. There's electric current. Okay. So let's start with it. A reaction A reaction taking place when a metal comes in contact with an electrolyte, releasing the metal ions into the electrolyte. What we say? A reaction takes place when a metal comes in contact with an electrolyte, releasing the metal ions into the electrolyte. However, very soon an equilibrium is established and the reaction does not proceed further. Okay, let's discuss once more again. It is a very interesting thing. A reaction takes place when a metal comes in contact with an electrolyte, releasing the metal ions into the electrolyte. However, very soon an equilibrium is established and the reaction does not proceed further. Now, if a dissimilar metal forms a second electrode, there will be a similar equilibrium at this electrode too. Now, if the circuit is completed, allowing the flow of current, the equilibrium is disturbed. Okay, now the circuit completed, allowing the flow of current, the equilibrium is disturbed. So initially let us consider copper as the first electrode, zinc as the second electrode, water as the electrolyte. What we are taking? Copper as the first electrode, zinc as second electrode, and water as the electrolyte. Now this arrangement is called as galvanic cell. So if all the current continues to flow, a less noble metal that is called as zinc in comparison to copper will gradually dissolve in the electrolyte. So firstly, the zinc will gradually dissolve in the electrolyte. Or in other words, zinc corrodes. In other words, corrode. Okay, so first of all, since less noble metal, that is zinc, will automatically gradually dissolve with the electrolyte. Or in other words, it will corrode. So zinc is the anode of the galvanic cell. Zinc is the anode of the galvanic cell. You can see the diagram also. Now the more noble metal, copper, will act as cathode. So the reaction that occur at the two electrodes are like follows like Z and gives Z2 plus the two electrons, like anode reactions, and copper will deposit on the copper throughout the following reduction reaction like Cu2 plus is 2E minus is C. Okay, you can see the reactions. You can see this galvanic corrosion happening here in the diagram also having anode as zinc and cathode as copper. Okay, and the electrolyte is water here. This now if cupric ions are not available in the electrolyte, the reduction at the cathode may still proceed through other reactions. What they say? If cupric ions, there is cupric ions, if they are not available in the electrolyte, the reduction at the cathode may still proceed through other reactions. The hydrogen ions may get reduced, resulting in the evolution of hydrogen at the cathode. Now you can see when the copper ions are formed, they say that if cupric ions are not available in the electrolyte, the reduction at the cathode may still proceed through other reactions. And they are given that 2H plus plus 2E minus gives H2. Okay, this is cathode reaction, that is hydrogen ions are getting reduced. Okay, so it is resulting in the evolution of hydrogen at the cathode. So alternatively, the reduction may take place through oxygen and water combining with the excess electrons. What happens? This reduction is taking place through oxygen and water combining with the excess electrons to produce hydroxide ions like O2 plus 2H2O gives 4E minus plus sorry O2 plus 2H2O plus 4E minus gives 4HON minus. So it is forming hydroxyl ions. Okay. So a galvanic cell may be set up due to the differences in concentration of the metal ions in the electrolyte. Say this galvanic cell may be set up due to the differences in concentration of the metal ions in the electrolyte. The potential difference, okay, and the rate of anodic metal will depend upon the relative positions of the two metals in the galvanic series. I will show you a table, okay, how this relative positions of metals are set in the galvanic series. So a galvanic cell set up due to such differences in metal ions concentration is also called as concentration cell. I repeat, a galvanic cell, you can say a galvanic cell set up due to such differences in metal ion concentration is called as concentration reaction. So following table, you can say represent the reactivities of number of metals and commercial alloys in seawater like galvanic sea. So the alloys near the top of the table are cathodic and unreactive, and where those at the bottom of the table are mostly anodic. So no voltages are provided. So interestingly, a comparison of the standard EMF and the galvanic series reveal a high degree of correspondence between the most relative positions of pure base metals. So just one thing is important in this that a galvanic cell may be set up due to the differences in concentration of the metal ions in the electrolyte. Okay, and a galvanic cell set up due to such differences. A galvanic cell set up due to such differences in metal ion concentration is called as concentration cell. Now, in a wide variety of environments, most metals and alloys are subject to oxidation or corrosion to one degree or another. Okay, in a wide variety of environment, most metals and alloys, these are subjected to oxidation or corrosion to one degree or another. That is, they are more stable in the ionic state than as metals. They are more stable in ionic state than as metals. So, in going from metallic to oxidized states, in going from metallic to oxidized states, thermodynamically, there is a net decrease in free energy. This is why essentially all metals occur in nature as compounds. Okay, this is why all metals occur in nature as compounds like oxides, hydroxides, carbonates, silicates, sulfides, sulfates. So there are two notable exceptions like gold and platinum. Okay, for these two metals, oxidation in most environment is not favorable. For these two metals, oxidation, okay, is most environment is not favorable. And therefore both of these two metals may exist in nature in the metallic state. Okay, I repeat once again. See, due to this, you can say, all metals, the metals that are occurring in nature normally as compounds like oxides and hydroxides and carbonates, silicates, sulfides and sulfates. So, but there are two notable exceptions like gold and platinum. Okay, for these two metals, oxidation in most environment is not favorable, and therefore, both of these metals may exist in nature in the metallic state. Both of these metals may exist in nature in the metallic state only. So, in order to reduce the galvanic corrosion effects, following measures may be taken. If coupling of similar metals is necessary, one may choose that two. One must choose two that are close together in the galvanic series. I repeat once again. If coupling of dissimilar metals is necessary, one may choose two that are close together in the galvanic series. Now, one should use anode area as large as possible. You can do with that. You choose the anode area as large as possible. Okay, and avoid an unfavorable anode to cathode surface area ratio. Okay, what they say? One should use anode area as large as possible and avoid an unfavorable anode to cathode surface area ratio. Now one should insulate electrically metals from each other. Okay, and connect electrically third metal to the other two. This is known as cathodic protection. So we were discussing about this uh, uh, galvanic corrosion effects. Okay, you can say that in order to reduce these galvanic corrosion effects, following measures that we taken, and the measures are like that one should use anode area as large as possible and avoid an unfavorable anode to cathode surface area ratio, and one should insulate electrically metals from each other and connect electrically third metal to the other two. This is known as cathodic protection. So this is like galvanic series table that is in front of you, and here it is showing you that the table is having increasingly inert cathodic in the starting, and you can see the galvanic series is like having platinum, gold, graphite, titanium, silver, and if you talk about stainless steel, then you have a particular grades of 316 stainless steel that is passive and 304 stainless steel also, and inconel, okay, that is nickel alloy, like, okay, a nickel chromium iron alloy, and then you have nickel obviously with you. And then you have monel with you, which is also nickel alloy. Then you have copper nickel alloys with you. Then you have bronze. Okay, then you have copper with you, and then you have brasses also, that is a copper and zinc alloy. Okay, and then again you have the input and nickel that are active there, and then you have tin and lead with you. So these are cathodic. Okay, increasingly inert. They are increasingly inert things like that. But these are cathodic. Okay, in the Galvanic series. Now let's talk about anodic series. Okay, these are increasingly active downwards. Okay, now we have with you 316 stainless steel as active and 304 is stainless steel as active, and you have cast iron with it, and then you have iron and steel, aluminum alloys, and cadmium and aluminum that is commercially pure. Okay, commercially pure aluminum. Then you have zinc with you. Then you have magnesium and alloys of magnesium. Magnesium and alloys of magnesium. These are some anodic material in the galvanic series. Okay, so you can choose from them as anode and cathode, whichever is appropriate as per the process. Okay, you can have aluminum alloys in this, and also you have aluminum commercially pure. Also, you can use it as anode. So this is really interesting to understand and learn. Okay, so let's go to the next slide. Now, corrosion of similar metals in contact with each other, like the galvanic cell, is rapid. So, if we avoid bad contact between dissimilar metals, you can avoid the corrosion of anodic metal. The corrosion of dissimilar metals in contact with each other, like the galvanic cell, is rapid. Okay, so if we can avoid that contact between dissimilar metals, we can avoid the corrosion of anodic metal. That is why in fabrication work, one prefers the composition of electrodes in case of welding. Okay, one prefers the composition of electrodes in case of welding, and of rivets in riveting should be of the same chemical composition as the base metal. Now this is something interesting because they say that we should avoid right contact between dissimilar metals. Okay, so we can avoid the corrosion of anodic metal because it will corrode first. So that is why in fabrication work, when you're doing fabrication work, one prefers the composition of electrodes in case of welding, and of rivets in riveting should be of the same chemical composition. What they say? It should be of the same chemical composition of as the base metal. So galvanic corrosion also found to occur on the unprotected steel of ships due to the selective action of steel on the brass screws. You can see this galvanic corrosion also occur on the unprotected steel of ships due to due to selective action of steel on the brass screws. So an underground pipeline that passes through impervious clays in some regions and through porous sands in some other regions may corrode in the clay region. The galvanic cell may also be formed due to the different residual stresses in the same metal. So the stressed regions is more active. The stressed region is more active and is anodic with respect to the stress-free region. I repeat, the stressed region is more active and is anodic with respect to the stress-free region. So the types of galvanic cells are called as stress cells. Okay, there are stress regions which is more active and is anodic with respect to the stress-free region, and such types of galvanic cells. These are called as stress cells. So such type of cells can be formed between regions of different dislocation. What they say? Such type of cells can be formed between regions of different dislocations density in a cold worked metal or in polycrystalline metal, where the grain boundaries are anodic to the interior of the grain. Interestingly, a bent wire is likely to corrode at the bend where it has been plastically deformed. Okay, now corrosion rates. Now, the rate of material form removal as a consequence of the chemical attack or the corrosion rate is an important parameter. I repeat, the rate of material removal as a consequence of chemical action or the corrosion rate is an important parameter. So one can express this as the corrosion penetration rate. What do you call as a corrosion penetration rate? Okay, one can express this as corrosion penetration rate CPR, or a thickness loss of material per unit time. So it is expressed as CPR is equals to AW upon rho A. Now where W, capital W, is the weight loss after exposure in time t. What do you call as capital W? Capital W is the weight loss after exposure. Rho and A represent the density and the exposed specimen area. K is constant. Its magnitude depends on the system of units used. So for convenience, CPR is expressed in terms of either mils per year, that is MPY, or millimeters per year, like mm per upon year. Okay, so this is corrosion rates. You should understand this because this formula, because it will be helpful in the numericals. Okay, let's go further. Now, specific forms of corrosion. Now, we need to go with the specific forms of corrosion. Now, one can conveniently classify corrosion according to the manner in which it is manifest. So, usually, metallic into 8 different forms. What is it? Metallic corrosion is classified into 8 different forms. One is uniform, another is galvanic, then clear-wise, pitting corrosion, intergranular corrosion, selective leaching, erosion corrosion, and stress corrosion. So in addition, there is hydrogen embrittlement also. You can see this metallic corrosion, it is classified into different forms. Okay, like uniform corrosion, galvanic corrosion, clear-wise corrosion, pitting corrosion, intergranular corrosion, selective leaching corrosion, erosion corrosion, stress corrosion, and also there is hydrogen embrittlement. So, the truly speaking, this hydrogen embrittlement is a type of failure rather than a form of corrosion. This hydrogen embrittlement is a type of failure rather than a form of corrosion. So, however, hydrogen embrittlement is often produced by hydrogen that is generated from corrosion reactions. Now, let's talk about uniform corrosion first. Okay, this is a form of electrochemical corrosion that occurs when the whole surface of a metal is corroded to the same degree and when the metal surface and the environment are uniform. I repeat, this is a form of an electrochemical corrosion, this uniform corrosion. This is a form of electrochemical corrosion that occurs when the whole surface of the metal is corroded. Okay, when the whole surface of the metal is corroded to the same degree and when the metal surface and environment are uniform. So this type of corrosion often leaves behind a scale or deposit. This type of corrosion often leaves behind a scale or deposit. Now, under these conditions, one can easily estimate the useful life of a given material, and there is no need to fear about unexpected failure. There is no need to fear about unexpected failure. One can easily control the uniform corrosion attack. One can easily control the uniform corrosion attack by selecting suitable material. Okay, no one can easily estimate the useful life of a given material and there is no need to fear about the unexpected failure. So one can easily control the uniform corrosion attack by selecting suitable material. So in such practice, the corrosion is rare. Uniform corrosion is generally observed in metals like zinc and maybe and aluminium. Okay. Now, clear-wise corrosion. This is also very important type of corrosion, and we have been discussing about corrosions. So I think this we will discuss in our coming lectures. So let's start with the MCQs. Okay, MCQs are also important, and that should be completed also. Let's start with the MCQs first. Okay, the MCQs for today's lecture are. Excuse me. Let's start. Corrosion is defined as the destructive and unintentional attack of a metal. What do you say? This corrosion is defined as the destructive and unintentional attack of a metal. It is electrochemical and ordinarily begins at the surface. It is true or false? So we have been discussing about corrosion in detail in our previous slides. And also it was understood there only that it is a kind of a destructive and unintentional attack of a metal. Okay, so I think it's true. The answer is true in this case. A is the answer. The ferrous alloys that get rusted at high temperature form scales and oxides. So one can prevent this corrosion by adding alloying elements which are resistant to oxidation in some metals and can also have good properties of high temperature service. See, this is a prevention technique. If you want to avoid corrosion, you can alloy elements that resist oxidation. Okay, and save the metal from getting oxidized or avoid corrosion in that. So this is true. This is true in case of ferroalloys. This is true. Okay, the answer is A. The ferrous alloys you get rusted at high temperatures from oxides and scales. So you can prevent this corrosion by adding alloying elements which are resistant to oxidation in some metals and also have good properties at high temperatures. So answer is true. A is the answer. Okay. The third question. In electrochemical corrosion, the site at which the oxidation takes place is called as anode, and the oxidation is sometimes called as anodic reaction. That is true, obviously true. We have discussed before also that when we talk about corrosion, so when the oxidation is taking place, it's called as anode, and the oxidation, the process that is called as anodic reaction. So I think it's true in this case. The answer is A. Now, electrochemical corrosion, this is kind of corrosion that develops in liquid electrolytes and moist atmospheres, in soil, in salt, in fresh water, in aqueous solutions of salts, alkalis, and acids. And we have discussed a lot about electrochemical corrosions in our lecture. So I think this is true. This is true in this case. The answer is A. We can also define this as this kind of corrosion, this electrochemical corrosion. Okay, this kind of corrosion develops in liquid electrolytes. Okay, and in moist atmospheres, in soil and salt and fresh water, aqueous solutions of salts, alkalis, and acids. So electrochemical corrosion holds true. This statement that is of electrochemical corrosion, this holds true. Okay, the answer is A. Moreover, the basic you can say the concept behind this discussion about this statement is that for electrochemical corrosion, we should understand that this kind of corrosion is develops in liquid electrolytes or in moist atmosphere. So you take care of this, okay? Like in soil, salt, and fresh water, you should aware of that, and aqueous solutions of salt, alkalis, and acids. So these all conditions are should be known to you, okay, for this corrosion process. Now, electrochemical corrosion is characterized by the appearance of an electrical current and the dissolution of a metal due to the electrochemical interaction with the electrolyte. I think it's true in this case. The answer is A. Answer is true. So, in a galvanic cell, this copper acts as the first electrode, and the zinc is acting as a second electrode, and water as the electrolyte. We have discussed in detail about this galvanic cell in our lecture. I think it's true. Answer is A. A galvanic cell set up due to such differences in metal ion concentration is also a concentration cell. I repeat, a galvanic cell set up due to such differences in metal ion concentration is also called as concentration cell. The answer is true, A. A galvanic corrosion also found to occur on the unprotected steel of ships due to selective action of steel on the brass tubes. So answer is true in this. I is the answer. An underground pipe that passes through impervious clays. I repeat, an underground pipeline which passes through impervious clays in some regions and some porous sands in some other regions may corrode in clay region. So galvanic cell may also be formed due to different residual residential stress in the same metal. So answer is A true. The rate of material removal as a consequence of chemical action is called the corrosion rate, and is also a very important parameter. Obviously, we discussed a formula based on that. Also, answer is A. True is the answer. So we have discussed a lot about this corrosion, and maybe we have discussed about types of corrosion. So I want you to refer these books also. And these books will provide you deeper knowledge of these topics. Okay. Moreover, we have faced corrosion in normal day-to-day as examples also. So, but if you refer these references, obviously these books will give you a wide knowledge about these topics. Moreover, you will have some more images that will give you a better idea of these topics. Thank you all.